So far, we've looked at incomplete information and used the concept of a Bayes-Nash equilibrium to understand simultaneous move games where there is incomplete information. Sequential rationality and subgame perfection are the tools we use to understand games where players move sequentially. What we'll do here is try and look at games where not only do we have incomplete information, but players also move sequentially. Let's start with an example. This game here is a variant of the gift game that we saw earlier. The big difference is that player 2 prefers to accept a gift to rejecting a gift, whether it's an enemy or a friend. It's just that the player 2 prefers the gift from the friend to the gift from the enemy. Player 1's payoffs are exactly the same, depending on whether they give a gift or not, depending whether they're the friend or not. As before, player 1's a friend with probability p, and an enemy with probability 1 minus p. The first thing I want you to notice about this game is that there's no proper subgame. The only subgame of this is the whole game itself. So subgame perfection doesn't help us much here. In particular, the strategy profile, neither friend nor enemy will give a gift, and the player 2 will reject the gift. This is a Nash equilibrium. And given that it's a Nash equilibrium, because there's only one subgame, the game itself, it's subgame perfect. But does this actually make any sense? 2 always prefers to accept than reject. The only reason 2 is rejecting here is because we never arrive at this information set. If we actually ended up at that information set, nothing could compel player 2 to reject the gift. So the only reason player 2 is rejecting the gift is because player 1 is not giving the gift, and the only reason both types of player 1 are not giving the gift is because player 2 is rejecting the gift. So for this game, it doesn't really make any sense for NF, NG, and reject to be an equilibrium. It's a Nash equilibrium. Since there are no proper subgames, it's also a subgame perfect equilibrium. But I think we can agree that sequential rationality isn't meaningfully satisfied here, because if we arrive at this information set of player 2 would not behave in this manner. So what we need to do here is to strengthen our idea of sequential rationality. Just the idea of subgame perfection isn't enough. The key idea in how we're going to strengthen sequential rationality is to introduce this notion of a belief. We're going to add the idea of a belief to the description of an equilibrium. A player's belief at a given information set is a probability distribution over the decision nodes in that information set. So it's also a probability distribution, conditional on reaching that information set, on the types of the other players. So if we reach a given information set, for example here, if we reach this information set where player 2 is playing, a belief would be a probability distribution Q1 minus Q, which gives us the relative probabilities of the different nodes in the information set. Player 2 only knows that they're in that information set, but Q tells player 2 what the relative likelihoods are of being at the different nodes in that information set. And that's what allows player 2 to decide what the best course of action would be. So let's see how these beliefs should be built and where they come from. What does player 2 know at the outset? Player 2 knows only that player 1 is a friend with probability p and an enemy with probability 1 minus p. This is what we call 2's prior belief about 1's type. We use the word prior here because it's prior to observing any of 1's actions. After all, player 2 will observe player 1's actions and infer information about player 1's type. After observing 1's actions, 2 can infer something about 1's type. Based on what player 2 observes, player 2 can update their belief. This is called an updated belief. We call this an updated belief, or often we call it a posterior belief. I'll try to stick to the term updated, but in the literature we usually use the word posterior. So how would 2 update her beliefs about 1's type? Well, it depends on what 1's strategy is. So how 2 updates her beliefs depends on 1's strategy. For example, let's suppose player 2 expects player 1 to play the strategy NFGE. So friend type doesn't give, enemy type gives. In this case, player 2 only expects to receive a gift from an enemy. So if she receives a gift, she can infer that player 1 is an enemy. In general, based on the strategy that player 2 expects player 1 to use, she'll update her beliefs. So now, given our definition of beliefs, we can refine our concept of sequential rationality. We can now define sequential rationality as follows. At each information set, the player who is called to play chooses the optimal action given her updated beliefs. In the particular example that we've just seen, sequential rationality would say, no matter what your belief Q is, player 2 ought to play A. So we can then see that the candidate equilibrium that we saw, which was a Nash equilibrium, isn't actually sequentially rational in this more refined way. Let's pull up the version of the gift game that we had seen earlier and see what sequential rationality would tell us there. So our earlier example looked like this. It's pretty much the same game. The only change is that player 1 doesn't like to receive a gift from an enemy, so it prefers to reject the gift from the enemy rather than accept it. Otherwise, everything is exactly the same as the game we just saw. Here, suppose that conditional on arriving at their information set where player 2 is called to make a decision, player 2 believes with probability q that they're at the top decision node, and with probability 1 minus q that they're at the bottom decision node. What's the expected payoff from playing reject given these beliefs? For any beliefs, if they play reject, they always get 0 no matter which node they're at. So no matter what q is, they're always going to get 0 as their expected payoff from playing reject. Her payoff from playing A is the following. If they're at the top node and they play A, they get a payoff of 1. If they're at the bottom node and they play A, they get a payoff of -1. So the expected payoff is probability of being at the top times 1 plus probability of being at the bottom times -1. The belief that player 2 has that they're at the top, given that they're having to make this decision, is q, and the belief that they have that they're at the bottom is 1 minus q. So their expected payoff from playing A is q times 1 plus 1 minus q times -1, which is 2q minus 1. So when is player 2 going to play A? In order to play A, 2q minus 1 has to be at least as good as R. So if q is bigger than a half, then only A is sequentially rational. If q is less than a half, then playing A would yield a strictly negative payoff, so only R would be sequentially rational. And if q is exactly equal to half, then player 2 gets the same expected payoff, so they're indifferent between the two, and they're both sequentially rational. Now, where did these q's come from? From where do beliefs generally come from? Can player 2 just have whatever belief? Can q be anything? For example, if player 1 strategy is NFGE, so enemy type gives, friend type doesn't give, does it make sense that q would be 1, for example? In fact, would anything other than q equals 0 make sense? No, it wouldn't make sense. If we go back to our picture here, if player 1 is playing this strategy, the only belief that makes any sense is that player 2, having arrived at this information set, believes that the probability of being at this node is 1. There can't be any positive probability that player 2 puts on that node, because that wouldn't be consistent with the strategy NFGE. In general, beliefs are updated according to Bayes' rule. We call this consistency of beliefs. Beliefs have to be consistent with the strategies. So beliefs ought to be updated from the prior according to the strategies that are being played. In particular, they have to be updated using Bayes' rule. Let's do a little aside here to remind ourselves what Bayes' rule says. Let's suppose you have two events, A and B. Bayes' rule says that the probability that A will happen given that B has happened is the probability that B given A times the probability of A, the whole thing divided by the probability of B. So put that in your pocket for now, and we'll use this as we go along. Important to note, this only applies if probability of B is not 0. If probability of B is 0, then we've got a divide by 0, which we can't have. Let's come back to our example here. In total, there are 4 things that you could observe. You could have an enemy giving a gift, while represented by E give. You could have E not give. You could have F for friend give, and you could have friend not give. So there's 4 different things that could happen. So let RE be the probability of E give, and let's let RF be the probability of F give. So if type F player plays GF with probability alpha F, and if player 1 of type E plays GE with probability alpha E, then RE would be the probability that player 1 is an enemy and gives. Remember, if we want 2 events, we take the product of the probabilities. So its probability that it's an enemy is 1 minus P. Probability that the enemy gives is alpha E. So the probability that an enemy is giving you a gift is 1 minus P times alpha E. And RF is the probability that it's a friend times the probability that that friend is giving you. So it's P times alpha F. What's the probability that we end up at player 2's information set if this event happens, or if this event happens? Since both of these involve not giving a gift, we don't end up at the information set where player 2 is called to make a decision. So it has to be that either this or this happens for us to end up at player 2's information set. So the probability of arriving at player 2's information set is simply the probability that one of these two things happens. And that's just the probability RE plus RF. And just so we know that that's clear, let's go back to our picture here. To end up at this information set, either we can go that way or we can go that way. So either nature picks enemy and enemy type picks give, or nature picks friend and friend type picks give. Those are the two ways that we can end up at this information set. So the probability that we end up here is the probability that either one of these two things happens. So let's work through a bit of an example here. Suppose RE were a 16th and RF were an 8th, then the probability of ending up at player 2's information set, so the probability of either E give or F give, is 3 over 16. However, conditional on arriving at that information set, what's the probability that you're at the top node versus the lower node? Let me go back to that picture again. If this occurs with probability 1/8 and this occurs with probability 1/16, what is the probability that you here versus here? This is twice as likely as this, because this probability is twice as much as this. So conditional on actually getting to this information set, the probability of being here is twice as likely as the probability of being here. So Q would have to be 2/3. In general, rather than looking at specifically RE equals 16 and RF equals 8, we would use Bayes' rule. So Q equals RF over RE plus RF. So it's the relative probability of arriving at the top node compared to the bottom node. So we divide the probability of getting to the top node by the total probability of arriving at the information set. Q is the probability of the type being friend given that you received a gift. Well, what are these things in this term? The denominator is simply the probability that you received a gift, because RE is the probability that you got a gift from an enemy, RF is a probability that you got a gift from a friend, so the sum of those is the probability that you got a gift from either a friend or an enemy, so it's just the probability that you got a gift. The numerator, recall, is P times alpha F. Remember, alpha F is the probability with which a friend gives. So that's the probability with which you'll get a gift given that it's a friend. So we could instead write it this way. Probability that you'll get a gift given that the type is friend. And P is simply the probability of a friend. So this thing right here in the middle is much easier to remember, but it's really just Bayes' rule. Now there's one little complication here. What if RE equals RF equals 0? So neither type is going to give you a gift. What should Q be? We can't divide by 0. Well, what we do here is we say Bayes' rule is not helping us out. So sequential rationality simply requires that player 2 have some belief. It could be any belief at all, but it has to have some belief and act optimally with respect to that belief. So the belief can be absolutely anything. Now it turns out that this can lead us to some funny places, and there's a whole literature on refining beliefs and having what are called reasonable beliefs, but we won't go down that road. It's a bit beyond the scope of this course. There's a whole literature on it, and if you're interested in it, you can read more about that. Cho and Krebs, for example, have some of the earliest work on this. Let's now put together our ideas of sequential rationality and beliefs to define a concept of a perfect Bayesian equilibrium. Perfect Bayesian equilibrium is comprised of a strategy profile and beliefs. The strategy profile sigma tells us what each player does at every information set. Oftentimes we represent beliefs by mu. In our example we've used Q, but generically we'll use mu. The belief says at every information set what is the relative probability that the player assigns to the different decision nodes. So these strategy profile and beliefs have to be such that at each information set, first, if I is called to play, then sigma I specifies an optimal action with respect to everybody else's strategies and the beliefs. And second, the beliefs are derived from the prior and sigma using Bayes' rule whenever possible. That's what a perfect Bayesian equilibrium is. So for a perfect Bayesian equilibrium, you have to specify not only the strategies, but also the beliefs. Now there are two important categories of behavior according to which we can classify equilibria. The first is what we call separating behavior. This is where each type behaves differently. So for example, in the gift game, NF and GE is a separating strategy. Similarly, GF and NE is also a separating strategy. Note that in a separating equilibrium, the posterior, or the updated belief, is fully informed. So if player 1 is playing one of these two strategies, then player 2 knows exactly whether player 1 is a friend or an enemy if we reach their information set. So if this is the strategy player 1 is playing, and we reach player 2's information set, player 2 knows that if they received a gift, it had to be from an enemy. Similarly, if they're playing this strategy, then if they receive a gift, they know it's from a friend. So the updated belief is fully informed when the behavior is separating. The other type of behavior is what we call pooling behavior. All types do the same thing. Examples of this are NF and E, so neither type gives, and GF and GE, so both types give. Again, in this case, the updated belief is exactly equal to the prior. And the reason is because the action that player 1 takes in this example didn't reveal anything. Both types didn't give, or both types gave, so by observing that action, I can't infer anything. There's nothing to learn. Typically, when we try to solve for a perfect Bayesian equilibrium, we'll first look for either a pooling or a separating equilibrium, and then try the other. So what I'd like to do next is solve for the perfect Bayesian equilibrium of this gift game that we had seen. Specifically, we'll look at this one, not the modified one we saw first. So this is the one we had seen earlier. We'll solve for the perfect Bayesian equilibrium of this game. What we're going to do is try each possible strategy for player 1 and see if that could be part of an equilibrium. We'll first start with the separating strategies, and then we'll try the pooling strategies. So let's start with NF and GE. When we update using Bayes' rule, the only way we end up at player 2's information set is if player 1 is an enemy, given that player 1 is using this strategy. That means that Q has to equal 0. So the probability of being at the top decision node in player 2's information set is 0, because that's the one where player 1 is a friend. Player 2 knows for sure that player 1 is an enemy should player 2 receive a gift. So player 2 is going to play R. Remember that we solved earlier that sequential rationality says that player 2 plays R if Q is less than or equal to a half, and plays A if Q is greater than or equal to a half. So 2 plays R, but if player 2 plays R, then the enemy type isn't going to give. They'd prefer not to give. So it can't possibly be a perfect Bayesian equilibrium. So since player 1 would prefer not to give, rather than adhering to this strategy when their type is E, this can't possibly be a perfect Bayesian equilibrium. Now let's try GF and E. Again, updating using Bayes' rule will tell us that Q has to be 1. Because the only type giving is the friend type. The enemy type doesn't give. So the only way you end up at player 2's information set is if player 1's type was friend. Given that Q is 1, player 2 is going to play A. But then the type E of player 1 would prefer to give rather than not give. So when player 1's type is enemy, they wouldn't do this. They would actually prefer to give. So this can't be a perfect Bayesian equilibrium either. So what we can see here then is that there's no separating equilibrium. So let's try the pooling strategies. The first of the pooling strategies is where they both give. So both friend and enemy types give. Because it's a pooling strategy, when we update the beliefs using Bayes' rule, the updated belief is exactly equal to the prior. So 2 will play A if and only if P is greater than or equal to a half. If P is less than a half, 2 plays R, so neither friend nor enemy type of player 1 would want to play give, since 2 would reject. So neither type would adhere to GE-GF. So if P is less than a half, this can't be a PBE. However, if P is greater than or equal to a half, then we know that 2 plays A, and both types of player 1 are happy to give rather than not to give. So they adhere to this strategy GF-GE. So when P is greater than or equal to a half, Q equals P, and the strategy profile GFGE and accept form a PBE. Now there's one more strategy that we can try for player 1. Neither type of player 1 gives. This one's tricky. We can't use Bayes' rule. Bayes' rule doesn't apply because we reach player 2's information set with 0 probability when neither type is giving. So we can't find Q. Remember, Q is probability of friend given that you got a gift, which is the probability of getting a gift given friend times probability of friend divided by probability of getting a gift. But probability of getting a gift when neither type is giving a gift is 0. So we can't apply Bayes' rule. When you can't apply Bayes' rule, you can pick whatever belief you want. So any belief q is fine. If we pick some q less than or equal to a half, then we know that r is sequentially rational for player 2. So q less than equal to a half and nf and g along with r is a perfect Bayesian equilibrium. So we've then found that there's an equilibrium where both types of player 1 give, and there's a perfect Bayesian equilibrium where neither type of player 1 gives. So there are two pooling equilibria and there are no separating equilibria. The reason we don't see a separating equilibrium here is because when we look at the different outcomes, both types of player 1 have exactly the same preferences. So there's no way for player 2 to tease them apart. When you have at least some difference in the preferences of the different types of a player, then you can sometimes see separating equilibria. But when they have the same exact preferences like this, then the only equilibria typically are pooling equilibria. In the next video, we'll see some more examples of solving for perfect Bayesian equilibria.